Hi, thank you everyone for coming. My name is Nicolas from Transfer Americas. So we're happy to see that many of you have chosen to register for this fourth webinar. As you probably noticed, we are now doing every other week, always on the Friday at 10 a.m. Central time. The topic for today is dive analysis. We have received also new ideas from you, so we'll thank you for that. We'll do our best to address all those topics in the coming webinar. Last point before we start, as mentioned in our email, we want this webinar to be interactive, so please do not hesitate to use the chat feature to ask your questions since we have muted everybody. I will monitor the questions and answer on the go. Today we will review the different approaches, uncoupled and coupled, pre-stressing, thermal steady state, and introduce a model for Wear Computation. So both new and experienced users are going to benefit from this webinar. And with that being said, I will let Sergio Rodriguez, our technical support engineer, lead this webinar. Sergio, go ahead.
All right. Thanks, Nicolas. Hi, everybody. As Nicolas said, this week we're going to get into detail with dye analysis and all the tools we have in Forge to tackle this issue. A quick introduction. I'm going to start giving a quick review of the main defects we can expect in dyes. Then I'm going to show the three approaches we can take to simulate these defects: rigid approach, uncoupled computations, and coupled computations. Once we know the tools we have, I'll talk about how to pre-stress the dyes before we launch our simulations. I will review the thermal steady state template so we know how to launch these simulations as well. And then I will give a quick introduction with the main techniques we have for Wear Computation. So let's start with the introduction. Here we can see the four main defects we're going to see in dyes: mechanical fracture, mechanical fatigue, wear, and thermomechanical fatigue. We're going to be able to simulate all of them in Forge. Here we have some quick statistics of the damage we see the most. It's normally wear, and the typical places in the dye where we see the different defects. This is just an example. So now to address those, to identify those defects, we'll have three approaches: rigid approach, uncoupled computations, and coupled computation. Starting with rigid approach, this is just the standard template we run with Forge, where we have a deformable part or billet and two rigid dyes. That's the normal setup for most forming simulations. Here, the dye formation is not taken into account and its temperature is considered constant. So that's the first assumption, very important assumption. However, we will still get results for the dyes. How this works is we compute the results in the billet, and then we extrapolate them to the nodes in the external sulfur of the dyes. The main results we're going to see in the dyes are the abrasion wear, contact time, and normal stress. This means that it's important to get rid of the STL mesh we have by default in the dyes. A quick remesh with default values will get a standard mesh, and it will improve a lot the visualization of these results. I'm going to start showing these three results. First, we have the normal stress. This one will tell us where we have the compressive areas in the dye. The higher the values, the more compressive that area. Also, we can use this result to know where there's contact with the billet. A zero value means there's no contact. In this case, in the red area, we don't have any contact with the billet. Next, we have the abrasion wear. this result will tell us where we have the highest wear in our die. However, it's a qualitative result. We cannot take it as a quantitative result unless we do some real testing and we identify which value is going to create a defect in the real world. We need to look at our real world simulation and see when we start getting defects. We will see later when we can get an abrasion wear as a quantitative result. But the first one we see, it's qualitative. It will tell us the areas, but we cannot tell there will be a defect for sure. We just can tell that in these green areas we'll have the highest wear in our die. Next, contact time. This result will accumulate the time when the billet is in contact with the die. It can be a good indicator for thermal stress in processes with high heat transfer. Okay. These are the three results we get by default in the rigid approach. It's not a lot, but it's a good way to get some information really quick. Next, we'll see the uncoupled approach. The uncoupled approach is called uncoupled because it requires two simulations. First, we'll have the rigid approach simulation, the one I have just explained, one deformable object, the part, and two rigid dies. Once this simulation is done, we will create a new simulation. We will import the die we want to analyze, let's say the lower die. We need the die to be in the same position and with the same mesh. Because we are going to import those results I just shown, the abrasion wear, contact time, and normal stress, through DR3 files. These are stored automatically by default when we run a rigid approach simulation. We will import those results in the external surface of the die in our new simulation. So it's important that we keep the same meshing in the external surface. It will improve the results, the importing of the results. Okay, so once we import the geometry, we'll need to remesh it, but it's important to keep the same mesh size. Once this is done, we will have to add a rigid die just to add the mechanical boundary conditions. And with this done, we can run the simulation. It's a really quick simulation. Sometimes it takes 1 or 2 minutes, depending on the process. This one took less than 1 minute. It's a 2D simulation. Normally, it's really, really fast. The main limitation here is that we are only working with mechanical results. There's no thermal results involved. And as I said before, in the rigid approach, we are assuming that the temperature is constant in the dies. So this means every result we see in the die stress analysis computation, the second simulation, will be independent from the temperature. So it's a big assumption. Still, it's a really quick simulation, and it will give us a lot of information to estimate the stresses we are to expect in the die. Also, the billet is not modeled, as you see. It's going to be only the dies. So we won't be simulating the interaction between the objects. It's also a big assumption. The results will be only in the dies. And we can expect some differences when we interact. If we run the whole simulation as deformable, we can expect some differences in the results. Still, it's most times you get a lot of information. So normally, this is our go-to for the first analysis to give us an idea. If we see high stresses, we can go then with the next level of simulation, which is running everything as deformable. But starting with this is a good strategy because it's a really quick simulation again. I'm not going to get into how to prepare the setup. For that, I would recommend to check this new tutorial in the online help. Hope everybody is familiar with this. You can access it from the new interface. Clicking help, this will take you to your browser. Here, if you go to tutorials, diameter computations, and coupled simulation, you will see a step-by-step guide about how to set up this simulation. I'm going to review the typical results instead. First, displacement. This can be used to estimate the deformation that we can expect in the die. We can have it by axis. In this case, I'm showing the displacement along C in this die. Or we can show the norm of the displacement field. You have the equation here, and it will give us an estimation of how much the elements are being displaced. Next, we will have the von Mises stress. Here we will also have deformation if we go over the material elastic limit. This simulation includes the elastic and plastic regions in the stress-strain curves. This means if the stress is really high or higher than the material elastic limit, we will be able to see some deformation. Okay. Next, once we have reviewed the von Mises stress, we can get into the principal stress tensors. Normally, from the von Mises stress, we can get the areas where the stress is the highest. We normally consider those areas as the ones with highest risk to get a crack there. Once we have detected the risky areas, we can go to the first principal stress tensor to check if those areas are in tensile state or compressive state. If they're in tensile state, that's when we have the highest risk because the crack initiation will be a lot more likely to happen. By the way, we know that elements are in tensile state if we have positive values for the first principal stress. So in this case, we will be worried about this area in red because if you see here, we have a really von Mises stress, and also we have positive values for the first principal stress, which means high von Mises stress and tensile state at the same time. There's a high risk of crack in that area. The third principal stress tensor will give us information about the elements in compression state, but that's not as important to find areas with high crack risk, so we are not going to get into. Okay, next we have the first principal stress vector. This will show us the traction direction. We can also visualize vectors, so don't forget about that. We can use it to predict where the cracks or the direction the cracks will go. Normally, they will be perpendicular to the traction direction. So in this case, the cracks will, if we get a crack initiated there, it will grow in this direction, perpendicular to the arrows. Okay. A final comment here for the uncoupled computation. It's important how we choose to represent our dies. In this example, you can see we increase the thickness, kind of twice the value. Huge difference in the displacement in the model. I'm showing the maximum value. It's 0.37, and it goes almost to double this value with a higher thickness. Also, if we add, instead of just a plane, as you see here, or a sheet to represent the floor, if we use the whole, let's say, assembly here, we'll see a change in the distribution of the displacement. I just want to show this to bring awareness to represent the assembly properly. It's important that we represent the boundary conditions as accurate as possible. Okay, now let's get into the coupled approach, the most complete simulation we can run for die analysis. In this type of simulation, we'll have the billet as a deformable object as before, but now we will transform the dies into deformable objects. They won't be rigid anymore. They will be volumes with material, and the temperature will not be constant anymore. Here we are simulating now a complete thermomechanical coupling between billet and dies. We will have to add some support rigid dies just to simulate the boundary conditions. And the main advantage is the complete thermomechanical coupling. We will get all the results we get in the billet, we will get them in the dies as well. Also, we'll simulate the interaction between deformable objects, and everything will be done in a single simulation. We don't need to run two simulations as we did with the uncoupled simulation. The main disadvantage of this is that the simulation will be time consuming. It takes a long time to simulate the interaction between deformable objects, so we can expect way longer computational times depending on the specific simulation. Again, check the online help for tips in how to set up this. There's a complete step-by-step guide, and next to the uncoupled simulation, you'll find a coupled one. Something important in this type of simulation is the contact analysis. When we have several deformable objects, we will need to apply a master-slave algorithm to solve the contact analysis problem. What this means at the end of the day is that we need to have always a finer mesh in the billet than in the dies, okay? I'm not gonna get into details because we don't have a lot of time, but every time we have deformable dies and a billet, make sure that you have a finer mesh in the billet than in the dies wherever you have contact. It doesn't have to be everywhere. We're talking about contact analysis here. So yeah, something that it's easy to forget that makes, normally you will have to add several mesh sets in the model to make sure you keep this rule, okay? You don't get a finer mesh in the die. When you have, in this example here, for example, we have a radii, kind of a complex curvature. Normally we'll get a finer mesh there in the die to be able to just represent the geometry. So here, in this case, this is our billet. We will have to add a mesh set over there to make sure the mesh size is finer than this. Okay. Also, in coupled simulations, I want to convert to deformable die. This will allow us to directly transform a die into a deformable object. We just need to select the die in the die section in objects, go to advanced, and click in convert to deformable die. This will move the lower die, in this case, up, and will create a support die to import this or to create a support die for your deformable object, which is almost always required. I just wanted to mention this. It's only in the new interface. So for those old interface users, please try to move to the new interface as soon as possible. All the new features are being applied there. Okay, just wanted to bring awareness to this feature. It's really useful. It takes 30 seconds to set up your coupled computation. Okay, so now I'm going to just show the differences we can expect from the rigid approach to the coupled approach. First, we will see a difference in the material flow because now the dies are deforming. So this means will normally increase the inner volume or the cavity between the dies. This means normally the flash will decrease. So as you see, the flash decreases in this example. So yeah. Next, the normal stretch. The values normally are not that different from each other, but the distribution of values, it's a lot better. So we will improve the accuracy of this result. I'm going to have on the right the coupled approach always, and on the left the rigid approach. For the wear, normally as we reduce the amount of flash, we will have less wear due to that. So these results should be lower in the coupled approach. We can see in general the values have been lowered. Next, the von Mises stress. As now we are simulating the plastic area of the stress curve. So now the die will deform. With this, it will absorb some of the stress, and the values will normally decrease. Because in the rigid approach, again, the die cannot deform. It's a rigid object. This, as the von Mises stress will decrease, normally the displacement will decrease as well. Okay. In the rigid approach, we have an overestimation of the displacement. This is good to have kind of a safe factor for the displacement. Finally, it affects the forging load or the tonnage that we get in our simulation. Normally, in the coupled approach, we have a lower value due to the deformation on the dies that we have mentioned before, and the reduction on the amount of flash. Here in this example, we have 250 tons difference. And here I have a quick summary about showing the computational time that these simulations take. The rigid approach took approximately 45 minutes in the last example I showed. The uncoupled computation took just 30 seconds. It's a really quick simulation again. It, of course, requires to run the rigid approach first, so you can consider this pack as a 44 minutes plus 30 seconds. Making all the objects deformable took 2 hours and 10 minutes. You have the details of the machine used to run them. And again, it's the first question we get always is which approach is better. It depends on the available time we have and the course available. If we have the time and we have the computational resources, it's always better to run the coupled simulation because the accuracy will be the highest. But if we don't have a lot of time and we want to get a quick idea, we can go with the uncoupled computation and get a lot of information from it. Okay, so with this, we complete the review of the 3 approaches that we have to simulate die analysis. Now I'm going to talk about how to pre-stress before running our simulation. We have 2 techniques, one for 2D and one for 3D. In 2D, what we are going to do, well, first we have the typical case looks like this: billet, die, and the ring that is pre-stressing the die. What we do in 2D is we directly intersect the ring mesh into the die mesh. Then in the first computational increment, the mesh will adjust based on how much we have penetrated the ring into the die. Yeah, that's pretty much it. There's also details in the online help about how to do this in case you have questions, but it's just, again, intersecting one mesh into each other, into the other. Now, in 3D, we cannot apply this technique anymore in most cases due to this effect. The phase discretization we apply in 3D makes really hard to apply the intersecting mesh that we shown for 2D because the phases are not going to be coincident anymore. Okay, this will give a hard time to the remeshing module to work. To avoid this and speed up computations, because solving this problem in 3D will take a high amount of time, we came up with a virtual boundary condition that we call virtual interference fit. To apply this, we have to go to the die, Advanced tab, Free Surface Conditions, and we have to import the default set. Once we are there, we can go to Virtual Interference Fit. We will have to select one seed point, normally in the external surface, just to tell the software that we want to select this external surface, the die. Once we have selected the area we want to apply the virtual condition on, we have to give details about the external ring. So now this external ring is going to disappear. The object is not going to be needed in 3D. We can just simulate the billet and the die. This is a huge advantage because we are removing one deformable object from the model, making it a lot faster in terms of computation. Once we have specified the details for the ring, we can confirm it will act really similar to the penetration, but it will be done as a virtual boundary condition. We will have to solve the phase discretization problem, and it will act a lot faster. Really easy to set up and huge advantage for 3D. Now, I'm going to give a quick review about the thermal steady state template. First, I would like to start saying that there's a tutorial about it, a brand new tutorial, online help, tutorials, thermal steady state. I recommend to give this, review this. It's a complete guide about it, quite useful. Now I'm going to explain what it is. This template is an additional template we add at the end of our forging process. And it is used to simulate the change in the temperature distribution that we'll have in our dies after forging several parts. First, we'll simulate what happens when we forge. And then, using this template, we will be able to simulate what happens after several parts. There are some options for the template, but that's the idea. Simulate what happens after forging a number of parts. How this normally works, we will have our forging process. We should include, in this case, the resting time when we position the part. Normally, there's some time before forging while we prepare the machine. Then simulate the forging, and normally, right after forging the part, there's a lubrication stage that will lower the temperature in our dies significantly. So we have to simulate the whole process. Okay. Once that is done, it's simulation done as a chain normally. Again, for details in the setup, please review the tutorial in the online help. Once this is done, we add the thermal steady state template. In this template, the main input we're going to apply is the steady state computation. First, we will just import the die we want to analyze. In this case, will be the lower die. Then we specify the temperature convergency. This is the temperature that we consider valid to assume to confirm that we have reached the thermal steady state. So we will the template will simulate how many parts we have to forge until we reach if we use 2.5 degrees, it means the steady state will be reached once we get a difference lower than 2.5 degrees between two consecutive forgings in the maximum temperature of the lower die in this case. For this simulation, it took 14 parts. After forging the part number 14, and the next one we had a 1.2 degrees difference between the maximum temperature in the die. So the simulation stopped there. The main results you'll get is the temperature distribution in the die after forging the amount of parts that are required to get to the steady state. And we'll also get the maximum temperature in the die versus time. This is how it looks. It looks like the first ramp is for the resting time of the die of the part in the die. Then in the forging, we'll get a huge increase in the temperature, and then it will decrease due to the lubrication phase, and the process will repeat. Normally, we'll see how it increases until we reach the steady state, and it stays constant. You see between the two last parts, there's not much difference. That's when the simulation stops. We have an option to run this template for a certain number of cycles. If we want to simulate 100 cycles, we will get the temperature after 100 cycles, and we'll get the maximum temperature versus time as well. There are more details here. I don't have a lot of time for that, to explain that, but you can review the details in the online hub. And finally, a quick note in the Wear Computation. What we use normally by default is this equation. And as I said in the beginning, achieve results. It's a good way to estimate the areas that will have the strongest abrasive wear, but it's not a real measure of how much material we are losing. To achieve that, or to show that in the results, we have to use the RCAR model. It's a more advanced model that will allow us to visualize quantitative results. It will give us real measurements of the material we are losing from abrasive wear. The requirement to use this criteria is to have the beaker's hardness, it's here, is one of the terms, as a function of temperature. These require some experiments, but now we have a default library with some materials, with the curves for some materials. So it's a lot more accessible to use now. I'm going to show what we need to do to apply this model. But again, the main thing we need is the beaker's hardness as a function of temperature. To apply the model, all we have to do is add two user variables. I'm going to explain what these user variables are now. Yeah, in order to visualize this result in a die, the die has to be a deformable object. Okay? We need deformable for this. Okay. Now, the user variables that we have to define are the beaker's die hardness. As I said, we need this as a function of temperature. This is how the user variable looks. To import it, we'll have to go to the Store and Wear section. It's really easy to find. Once we import it, we'll have two options to define the hardness. First, we can import the curve if we have it. This is always the first option, hardness versus temperature. But now, as I said, we have some default materials. If you select the material type, it will import a curve automatically for that material. Okay, this is not 100% accurate because there are slight differences between the curve we are using and the ones you can have for the material, but it will be a good way to get a quick estimation. Right after that user variable, it's important we do it in order. So first, we need to import the beaker's die hardness and then the arc hardware. The arc hardware, we just have to import it. There's nothing to change there. It's possible to get into the advanced options and modify these coefficients based on your model. That's for advanced users that have a really high knowledge of their manufacturing process. To start with, it's enough with just using the beaker's die hardness, choosing your material from the material type, and then just importing the next user variable, arc hardware. Yeah, this is new, so I wanted to mention it. Has been applied in the new interface. Again, it will make this user variable more accessible, really useful user variable. Yep. With that, I have shown everything I wanted to show today. Quick reminder, please keep checking the online help. It has a search option to look for any topics you have questions about. We're adding new tutorials every week, new content pretty much every couple of days. Also, for people that want to get more detailed information, there's the reference documentation located by default in the documentations folder in your installation. It has a lot of advanced information, including most of the equations and formulas used by the solver. And don't forget that we are offering online trainings on demand. They are completely customizable, unlimited. You can have as many attendees as you want. And yep, really useful tool to get everybody up to speed for the new features. Now I will take any questions about die analysis.
Okay. Yeah, if you have any question, there's nothing in the chat during the presentation. So if you have any questions, please, it's the time now. Otherwise, as usual, you can always contact us at the support@translateramericas.com. Sergio, I'd like to thank you for this great overview of the die analysis in Forge. And I'd like to thank everybody for being here with us today. We hope we'll enjoy this webinar. Again, we have recorded this webinar and will be available for you in our member area. If you have not signed up yet, please go to www.translateusa.com and click on Members tab. Then sign up and we'll accept your request shortly after. We will communicate when the video is available. We're still working on the topic for next webinar. We obviously take into account your input and do our best to include them in our webinar. Our next webinar will be held in 2 weeks, still on Friday at 10 a.m. Central Time. We will keep this 2-week pace for quite some time. We will send the email announcing the new topics at the beginning of the week, and the webinar is held, so basically in 2 weeks. In the meantime, do not hesitate to contact us Should you have any questions, stay tuned, and thank you again for joining. You all have a great weekend. Thank you.